Good morning, everybody. Dr. Hoskins here. Appreciate you being here. Hope this is going to be something you're going to find some value in. Um, Hopefully, you'll enjoy it, if you will. I enjoy this kind of stuff because it's a science and it's truth and it's how the body works, and that's something that I've been very interested in for a very, very, very long time. Now, since we are in the South, I'm going to give everybody a little bit more time to get on here and see who's trying to get a hold of me. And see what's going on. And people are trying to call me already. How about that? All right. So we're going to be talking about the nervous system today. The nervous system well, we'll just get into it. We'll get into it. Let you see what's going on here. So the nervous system is the master control system of the body. I'm not going to read you slides. I hate it when people do that to me, but there's not much more to say here. It is the master control system of the body. And we need to understand what a control system is. So we're going to run through this real quick. This is just the way you can think about some things. So any organized structure has a decision that is made. Something, somewhere, some person decides to do something. And that is communicated to a processing unit, a part of the system that actually processes the decision and makes all of the choices on what to activate. It sends out those instructions to the target to perform some action. That action is performed, and then there's some monitoring that takes place. That monitoring is relayed back to the processing unit, and that processing unit sends that information, along with all the other information it's getting, back to the decision maker. This is a standard organizational structure. This is how businesses work. This is how the body works. This is how parts in the body work. This is how a cell works. This is how organelles within the cell work. This is just a diagram of the functions and the flow of actions within any system. This can be called a simple cycle, a simple normal cycle. If everything's functioning normally, this is going to be happening on a normal circle with another circle up here. So this is happening all the time, and this down here is happening all the time. Can you see my cursor? Let me see if I can get this. So this, no, that's not working. How about that? There we go. So that's working. That cycle there is working. And then, sorry about that. And then the cycle down here is working. And so this is a simple cycle, and that's what happens. Another thing we need to know about control system is there always includes two key components. Alarms. If this is functioning normally and the action or the monitoring shows that there's something going on, it will send back alarms to the processing unit. Now in the body we know the alarms is pain or achiness or heat or something that just triggers the body to respond in a certain way. In a house, an alarm could be a smoke detector, it could be an intruder alert, it could be any number of things that you have your alarms set for. So when an alarm goes off, that means the system is actually working normally. The problem comes if the alarm doesn't shut off like it's supposed to. That's when you have a problem in the control system. That's another topic for another day. The other thing is there's always must include an on-off. If let's say your heating system in your house kicks on when it's cold, that's what it should do. But if there's not a way to shut it off, eventually it'll just keep heating until it can't heat anymore, and your house will be 150 degrees. The other thing is if you kick on the cooling, when it gets too hot, it'll keep cooling. If it doesn't shut off, it'll keep cooling down to when it's very, very cold, so maybe 20 degrees. So there has to be on-offs, and those are all part of a normal system. So if a process starts normally, but then it continues past what is normal, the problem is not in the starting of the process. The problem is in interference with shutting it off. And so those are some things that you should be considerate of and knowledgeable about, and understand that there's always alarms, there's always on-offs in any system. All right, let's see what else we got here. So how do we know that the central nervous system is the master system. Here's some questions for you. So what tells the heart to beat? Yes, it's got some built-in nerve fibers. It's got a built-in pacemaker, if you will. They're called Purkinje fibers. And that tells the heart when to beat and how often to beat. But a heart can beat by itself outside of the body. But if the body theoretically started running, would the heart ramp up its output to take care of the body even though it's not connected to it? And the answer is no. The heart has to be connected to the nervous system to tell it how hard to beat, how often to beat, to sustain the body as a whole in whatever situation it is. So what tells the stomach to digest? Yeah, it has some internal sensors that when food is there, it starts to secrete the hydrochloric acid to break down the food and to do peristalsis, the squeezing to move the food and churn it up. But what tells the stomach to start, and part of that digestion is the nervous system. There's some feedback loops there. Sweat glands, what causes them to sweat? Again, the nervous system is telling it that, hey, we've got too much heat in the core. We need to get rid of some of that heat. And then this is when you need to stop. All right, what tells the ears to focus on? Now, that's on purpose. We think of focus as the eye function, but we can also focus with our ears. If you close your eyes and listen to everything going on around you, you'll realize that there's a lot more sound going on than what you are focused on. So the ear can't necessarily focus on that, but the brain focuses those signals on what is important. One of the things in martial arts that we teach our students is to focus on the instructor, focus on your opponent, especially when you're in that situation. But at a higher level, I tell my instructors to focus on the things not in front of you. How many people are in the room behind you? How many people are on the walking track around you? Those are things you have to focus on for situational awareness. And the ears, you can't do that without a brain, a master control system. And what tells your eyes to blink? Yes, there's some internal triggers, but you can stop those triggers. You can consciously say, I'm not going to blink, and try not to blink for a while. And you can tell your eyes to blink a lot, so you have some control over that as well. But here's a question. What tells the brain to think? What tells the brain to wonder or question something? What tells the brain? What tells you to create something out of nothing, or taking a pile of clay and making a vase, or taking a bunch of boards and making a deck, or taking a bunch of metal and some fire and making a motorcycle? What tells the brain to do that? And then what tells the brain which one of those options to choose? And so that's why the master system is the brain, the central nervous system, because it controls all the others. There is no question about that. It controls all of the others. So let's talk about another thing that we need to understand before we get into the instruction part of this presentation. The known versus the unknown. There's two things. So when you're walking down the sidewalk, you trip on a raised part of a slab. Why did you trip? Or let's even take it, why was that slab raised up? So the first question is, so the first observation, what you know is, oh, when I look down, I observe that part of that slab is raised up. And why was that slab raised up? The question is, what's pushing it up? What's pulling it up? And then let's uncover and see what's happening. So you dig, you look around, you do some observation, you do some discovery, you do some experimentation. And what you see is that you see a tree root pushing up that edge of the slab. Now you can say, okay, anytime a slab is uneven, that means there's a tree root pushing up. Is that true? No, there's other reasons for that. And so you don't want to just leave it there. So you ask some more questions. Well, why this part of the sidewalk? Why this tree? And then you do some more investigation. You do some research. You look at some other things, and you find out that trees use their roots to look for water and nourishment so that they can grow and become strong. But that doesn't really answer the question. Is why here? Why not over there? And why not other parts of the sidewalk? Why here right now? And there are some things that we just can't know yet. And that's one of the things that I want to really press into, especially when we talk about the nervous system, the master control system. There are so many things that we don't know yet. Theoretically, there are some things we may never know. But right now, we don't know everything there is to know. And I want to caution you, if you ever hear the statement that the science is settled, anything that comes after that, or anything that is about, automatically isn't science, because science is never settled. Science is always looking for the next answer. Science is always looking for the next problem to solve. That's what science is. So when you hear the science is settled, automatically becomes a non-scientific statement, just to let you know that. So material knowledge is what we know now. Immaterial knowledge is what we don't know yet, or what we may never know, and that's okay. Material knowledge are facts. Immaterial knowledge is facts that we don't know yet. We can guess about them. We can use some language about them. We can postulate about them, but we really don't know yet. Material knowledge is science. Like I said, it's a bunch of facts, a bunch of theories that have been proven or disproven that we know now. But science also is about what we haven't found out yet, and that includes some immaterial stuff. What we know is experiments, but what we don't know is things that we haven't even come up with experiments for, things we can't measure yet. And that's the next one. We can't measure it yet. There's a lot of things that we know now, and that's things we can measure, like how far the sidewalk is pushed up. Things we can see. Immaterial knowledge, this is weird because we may not be able to see it. We may be able to see it, but we just don't know yet. And it's one of those weird things. Until we can describe all of the facets of it, it doesn't become material knowledge. And then, material knowledge we can repeat. We can repeat the experiments. We can repeat the search for it. We can repeat the research into it. Immaterial knowledge, sometimes it can be repeatable. Sometimes it's not explainable. And the operative word here is yet. Some of the other known versus unknowns. Here's some examples. So, right now in 2020, March 18th, 2020, we know a lot about the DNA and the RNA in the nucleus of the cells. And that's taught as fact, and that's taught as complete science, and we know everything about it, even though there's people that spend their whole lives studying each one of these molecules. We're talking about things that affect how genetics are passed on. In the 1940s, that wasn't material knowledge. That was theory. That was what is this thing that's carrying on traits from one to the other. The traits that are contained and coded in the DNA were theorized long before that. And the monks did testing on sweet peas and fruit flies and stuff. But we didn't really know it until Watson and Crick in the 1950s. So was it true before it was discovered? And the answer is absolutely yes. We just didn't know how to see it or talk about it or describe it or see the actual mechanisms. And we're still don't know everything. We're still finding it out. Gravity. How long has gravity existed? And the answer is as long as there's been two distinct entities in existence, gravity has existed. But until Sir Isaac Newton came along, we didn't know it. We knew about it. We could see the effects of it. We could postulate about it. We could describe it, but we couldn't know its equation until Sir Isaac Newton described it and started working out those equations. The funny thing is, when Einstein came along in the theory of relativity, it totally rewrote those equations. And now with quantum mechanics and quantum theory, we're even rewriting the quantum stuff or the relativity stuff. So this is not even gravity is not set in stone. Pardon the pun. It is growing and changing as we become more aware of new stuff. Nuclear energy. We can observe the sun and we can make some postulations about it, but until Einstein and Opperman and those guys came along and came up with the theory of relativity of energy and matter have this relative relationship. E equals mc squared, if you will. We really didn't know how it worked, and we didn't know how to harness it. We didn't know how to use it until the 1930s, 1940s, when Opperman and Einstein and those thinkers started doing it. Now we know about fusion and fission, nuclear energy. We know about a lot of different things, but until the 1930s, 1940s, this was all immaterial because it wasn't known yet. So I wanted to walk through that because it's important to understand when we talk about the nervous system, there's some things that we don't know yet. We're finding that the impulses of the nerves aren't the message. The message is that the nerves are sending travel faster and are like a layer above the actual impulses of the nerves. The impulse of the nerve gets the energy down to the end of the neuron, but the message that's carried on that energy wave tells what neurochemicals to release. So there's some things that we're still finding out. And so I don't want to lead you into a false sense that I know everything or that everything is known, because we don't know yet. What we know, brain levels interact with each other at an extremely high level of specificity, accuracy, repeatability, and that they adapt, and they control a lot more than what we're aware of. And our future responses are dependent upon our current responses, and so we can adapt and learn. That's part of the material knowledge. We know that, but we just don't know how. We do know the chemistry, we do know the biology, but we don't know how, why, when, or any of that stuff yet. And even when we do know how, why, and when, there will be other layers of things that we don't know that we need to find out. And another thing we don't know about the nervous system, we don't know where the mind is, but we do see this concept of this thing that makes us us, that lives above our nervous system or anything that we can touch, taste, feel right now. But we see its presence and we see its effect. So it's an immaterial thing, even though we all know we have a mind and a conscience. All right. So the nervous system. Let's talk about the components of the nervous system. The basic component of the nervous system is the nerve cell. As with any cell in anything that has cells, from a bacteria all the way up to man or trees or cows or bats or alligators, you have certain components. You have a cell membrane, and that's the bag that the cell lives in. You have stuff within the fluid of the cell, the cytoplasm or axoplasm in the nerve cell. Excuse me, my allergies are acting up a little bit this morning. A nervous system over response to a stimuli. And within that cytoplasm, you have a lot of different organelles, or small organs within the cell. One of those organelles is the nucleus, and the nucleus is where the DNA and RNA reside, and that's where the instructions are decoded based upon what stimuli comes in, so that the cell responds accordingly to the instructions. If you remember that cycle, receives instructions and it acts, and then it responds back. So that's what happens here. The nerve cell has got some special components. So it has little feelers coming out. So you can see the dendrites, which are at the top center here. If you can see that yet. So the top center here, these are the dendrites. They're called dendrites because they look like trees. This is where these things are sensitive, if you will, to other stimuli. So these are the things that actually pick up the signals and transport it to the body of the cell. All of those signals, positive or negative, accumulate here, and if it's a positive, it'll cause a certain message to be sent down. If it's negative, it'll cause a depressive signal to be sent down. This axon, it's singular. It goes all the way down to where it touches other cells, and it could be a single cell, or it could be multiple cells. And this can be feet long. The longest nerve cell in the body are the ones that go to the big toe on your foot. That nerve cell body actually lives about midway in your back, behind your belly button, a little bit above your belly button. Then it has a part that goes all the way down your leg to your big toe. So these can be very long. The nerve signal transmits down that at about 33 feet per second. So if you have a 3 foot from your belly button to your toes, it's about a third of a second, or a tenth of a second. Sorry, can't do math right now. And that's how fast that impulse goes, and it also comes back that way on the sensory neurons. And it's the sensory neurons are flipped. The dendrites are that long, and then the axon is short, the message sending part. So if we just realize there's a nucleus, there's dendrites that bring in information, there is a singular axon which sends out information. Schwann cells, that's the insulation around the wire, if you will. And the Schwann cells produce this fatty substance called myelin. And then they have little nodes. And these nodes actually speed up the transport of the signal, because the signal will jump along these rather than go along each individual unit. They'll jump between nodes. And so it makes the transmission of the signal much, much faster. I think that's all we need to see here. See what we got here. Okay, so again, here's another picture of the neuron, the nerve cell. Nothing new here, just a different kind of drawing. And here's a microscope of how the transmission of signals happen. So you have axons from a neuron coming to the cell body or to the dendrites of another neuron, and they transfer information from one to the other. And what we see here are these little circles, these little spheres, and they're congregating right here where that synapse or that transmission area happens. These carry chemicals. Some are stimulatory and some are depressive. And depending on the signal coming down is which one gets released across that synapse to send a positive, a stimulatory, or a negative, a depressing signal to the next neuron. And so that's how the chemical reaction happens between neurons at the synapse, transmission of that signal. We're not going to get into that. That's neurochemistry, and I'm not prepared to do that. I would fall asleep talking to you about that. But that's where it happens. This is where the addictive things happen as well, because chemicals that you take into your body interfere with this synapse. Excuse me. So if you remember the cycle, we talked about on-offs. We talked about pain. So pain, again, is a normal thing. So if a body part is continually sending pain signals, blocking that signal can be viewed by the brain as a positive, as an enjoyable thing. And so when you get chemicals in there that block that pain signal right here, the brain rewards you with endorphins, which is a feel-good, happy thing you get when you have chocolate, or when you stretch really strong, you get that rush of really good feeling. Those are endorphins. And so the body rewards you when you do something to stop the pain. It doesn't stop the damage. It doesn't stop what's causing the pain to begin with. It just blocks the signal. And so that's how addiction can start. Then some of those chemicals actually cause a physical addiction. And when the body starts to decompose those, it causes some really, really bad things happening in the body. I'm not going to get into that. I just want to tell you this is where that happens on a large portion of addictive chemicals. And there's an artist's rendition. Again, you've got the little spheres being released and the chemicals going across the place to the other neuron. All right, so this is how a nerve works. When a nerve is at rest, which none of them are at rest for very long, but let's just stretch out the timeline. So when a nerve isn't doing anything, it's building up a resting potential. This is an electric charge, like what's in a battery. When you don't have a battery plugged in, it's got 3 volts. It's just AA battery. It's got 3 volts, or 1.6 volts, sorry. I'm thinking of a different battery. So AA's got 1.5 volts. At resting, it's got 1.5 volts. When you plug something in, or trigger something, that stimuli causes a release of that stored energy called an action potential. That action potential, that release of all that energy, travels to or in a neuron. Excuse me, my sinuses are stuffing up, so it's causing me to focus on how I'm going to get rid of that with talking to you guys. When that action potential is triggered, it causes a depolarization of that neuron, and that neuron then sends a signal for a synaptic release. So if it's a certain type of depolarization, certain chemicals are released. If it's a different kind of depolarization, different chemicals are released. And that's the message on top of the nerve impulse that we're talking about. But that depolarization automatically triggers a repolarization. Remember, we talked about in systems, you have an on-off. So the on was depolarization. The off was recharging the nerve back to this original state of a resting potential. So this is just a really simple diagram of how the nerves work, how the neurons work. And just kind of give you a simple idea of how a nerve works. That stimuli can be from outside. So if this is a sensory stimuli, let's say in your eye, that stimuli can be photons hitting your retinal cells, causing an action potential, depolarization. And the signal was, hey, I saw a blip of red. Repolarizes, get ready for the next red photon. Right, there's 3 main types of nerve cells. Again, I hate to read this to you, but there's ones that sense the environment, or it's either sensing the environment outside of us or sensing the internal environment. And so that gathers information and sends it back to the central nervous system. There's motor neurons, and that's taking the information and the decision and sending it out to the body or to the target cell. for it to do some certain function that it's telling it to do. Then you have the relay neurons, and that's relay neurons are mostly in the brain, talking between the sensory motor neurons, helping the decision to be made, so that um, you can do whatever's proper for the situation. So again, here we go back to our control system. If we just do this, we can see that the decision and the processing, these happen in the central nervous system. The action, the monitoring, the input and output, they happen in the peripheral nervous system. And in fact, here we go, central nervous system. The action and monitoring actually happen in the target cell, whatever cell that action is directed to. So if we need more insulin, that target cell is the pancreas. If we need to lift my coffee cup, that target cell is the motor, or to the muscle cells to lift my coffee cup. And then we have the efferent and afferent peripheral part of the nerve system. We'll talk about that in a little bit. But then we have this thing called the decision center of the mind. We don't know where that's at. Some things like automatic reflexes, those don't get to that high of a level. But deciding whether to drink, if I'm thirsty, do I drink one swig of water? Do I drink a cup of water? Or do I go and drink a half gallon of water? Those are decisions that the mind makes. So sensory neurons, again, receptor, this is the monitoring input. Motor neurons, this is where the action gets sent, action decision gets sent. And then the relay neuron, this is what happens within the brain. I already talked about that. We put these on the diagram, and there we go. That's what we have. All right, then we're going to talk about the different divisions of the nervous system. What I'm going to do is I'm going to take a little break here. We've already been 30 minutes into this. This is really crazy. Really, really crazy. But give me just a few moments. I'll be right back. I need to blow my nose, and hang in there. Won't be too long. Are we back? Are we back? Are we back? Are we back? I hope this has been working fine. Oh, that would break my heart if that wasn't working right. I think it was. All right, here we go. Nervous system. Are you okay? Oh my goodness. Sorry. Let me start that over again. Nervous system. Four main sections: cerebrum, cerebellum, the brainstem, and the spinal cord. I call the cerebrum and cerebellum together the brain. That is where we differ a little bit because, and I see their point. The cerebrum is the higher functioning stuff. This is memory, and this is processing things at a higher level, putting together sight and sound to trigger memories and things like that. And the cerebellum is more of your balance and coordination things at a lower level, things you don't really think about, subconscious coordination. Then you have midbrain, diencephalon, all these things here in the midbrain that are extremely low level processing. Not that they're not important, but they're just at a lower level of intensity, I guess. It's not an importance thing when I say low level, high level. It's just the complexity, I guess. And some of the things they do is extremely complex, like heart rate and blood pressure and all those things. The interesting thing is all of the cranial nerves come out of the midbrain and brainstem. And so that's really, really cool. And then you have the spinal cord. The cerebellum, conscious activities, memory, language, intelligence, uh, muscles. There's 4 lobes. The important thing to remember is it's protected by bone, and it's protected by 3 layers of tissue called meninges. The cerebellum, this is again where coordination happens. This is where, if it's injured, you lose coordination, you become jerky and lose your balance. A well-trained athlete has a well-trained cerebellum. When you look at gymnasts, their balance is extremely intense, and that is part of what the cerebellum does. And this part is also protected by bone, still within the cranium inside the skull. And it's also protected by the 3 layers of the meninges. We'll get that in just a little bit. The brainstem, it has different components that control different things. One of the interesting things, this is called a reptilian brain, and they called it that to begin with because it looks like it is the brain of a reptile. Even though it's not, it looks like it. And in fact, the entire brain of the reptile is basically midbrain's brainstem, and that's what it functions on. But it also controls the basic functions of life preservation that a reptilian brain would be interested in: finding food, staying protected, finding the things necessary for life and protection of life. And again, it's protected by bone, and it's also covered by the meninges. This bone is a little different because it's outside of the skull. The brainstem itself extends down into the 2nd vertebrae, sometimes the 3rd vertebrae in your neck. And so it is covered by meninges as well as for protection. Yeah, that's my mother-in-law. Say hi. This is a picture of the brainstem. This is the cerebellum. This is the where the coordination happens. And this gets down into the brainstem itself. The spinal cord. This is where I live every day. Brainstem and spinal cord is what chiropractors work on every day, making sure that the bones that protect them aren't pushing on them, causing misfiring or the malfunction of the nerve system. And again, the spinal cord, it's a continuation of the brain and the brain and the brainstem down your body. This is where all the spinal nerves come off. It's protected by bone, the vertebrae, and it's also protected by the meninges, all 3 layers, all the way down to the end. The meninges, you have 3 layers. You have 3 layers. You have the dura mater, which is a very tough thing. If you guys seen the house wrap that are on houses when they're being built, that really tough Tyvek is the name brand. That's what this dura mater is. It's very, very tough. It doesn't like to be tugged or pulled or twisted. If it does, it's like on a house. If you pull one corner of the Tyvek all the way across the whole entire surface, it gets crinkly. And so it does not like being torsioned. It doesn't like to be pulled. It doesn't like to be pushed on. It keeps a lot of the stuff out of the central nervous system that doesn't belong there. It also protects it, and it keeps it in its protective balloon. So that's an important part. That's an important meninge. It's the one that connects to the bones to kind of hold the balloon that the central nervous system lives in. It holds the balloon in its shape. So it kind of is the interface between the bones and the nervous system. So we have these little things that attach this dura mater to the bone, and then the other layers of the meninges connect the dura mater to the brain itself, the brainstem, spinal cord. The other arachnoid membrane, this is a really cool one because when you actually look at it, which I got to do in chiropractic college, it actually looks like a spider web. And it is kind of like the packing in a pillow, if you will. If your grandma or mom or brother, sister make pillows, and that packing, not the foam, but the fiber packing, kind of looks like that. That's kind of stretched out. And the fake snow. And the fake snow scenes are on the train. Model train areas, they put fake snow, that little fluffy fibery stuff. That's what the arachnoid membrane looks like, and it's wrapped around there, and it's there to protect. It gives some cushion, but also lets fluid flow freely. And this is where it creates the chamber for the cerebral spinal fluid to flow back after it travels down. It flows back on the outside of the brain, back up to the skull, and that's where it's reabsorbed. And then you have the pia mater, the little mater, the intimate uh, membrane. And this is the one that covers the nerve tissue itself so that it's protected and connected. Um, Nerves themselves are very like warm jello. They don't hold their shape very well. So the pia mater is that casing around them to keep their shape. So you have the pia mater keeping the nerves and the nerve system, central nervous system in shape. And then you have the arachnoid keeping the space open and flowing. And then you have the dura mater, which is connected to the bone and keeping everything in place. And these are extremely important, and it covers the entire central nervous system, brain, brainstem, and spinal cord. And they're very, very, very important when we do this, when we think about the central nervous system. All right, so that's the central nervous system. The peripheral nervous system, that's the stuff outside of the brain, the brainstem, the spinal cord. Anything outside of the bone protection is called the peripheral nervous system, and there's two divisions. You have the somatic or the voluntary, then you have the autonomic or involuntary system. So we're going to talk about the voluntary or somatic first. And that includes the cranial nerves. The cranial nerves come off of the brain or brainstem, and so we have 12 of those, and some are motor, some are sensory, and some are both. And our sight, our sense of smell, our sense of hearing, controlling our eyeball motion, controlling our balance, controlling how our lungs and intestines and digestion works, controlling our tongue and speech, controlling our face and head, and sensing what's going on in our face and our head. All of those things are controlled by the cranial nerves. They're called cranial nerves, like I said, because they come off of the brain and brainstem, and they come out of the cranium, so they're called cranial nerves. Some people call these just higher spinal nerves, because cranial nerve 1 comes out right below, spinal nerve 1 comes out right below cranial nerve number 12. So it's kind of a continuation, but that's what they called them, and so that's the nomenclature we keep. And here's a very, very simple diagram of the peripheral nervous system. You do have the brain, brainstem, and spinal cord there, but everything else is the peripheral nervous system. It's been said that if you took away every other cell in the body and just had the nervous system, you could still take a fingerprint, and you can still recognize that person in a crowd of other nervous systems. So every cell in the body is either directly or very closely directly connected to the nervous system. And I say that understanding that we have blood and we have lymph fluid that flows, since we have cells flowing in channels. Yes, those are intimately, either directly or very closely directly affected by the nerve system on a regular basis. So this is why, another reason why the central nervous system is so important. And it is a master. So here's a very, very rough diagram of how the peripheral nervous system works. You have a sensory receptor that sends information into the spinal cord. In the spinal cord, since it's in the central nervous system, we have these interconnecting neurons. They don't only interconnect from sensory to motor, but they go up and down in tracks to go to the brain for higher level processing. But in a reflex arc, you step on a tack, it causes the muscles to contract to pull you away from that stimuli. We also have a connection here on proprioception or position sense. So when anything moves, it creates an arc, so we know when to stop moving. And again, this is a system. This is a loop, and that loop has another loop attached to it for a simple normal cycle. So again, this doesn't have to be a tack. This could be smelling bread baking, and of course that's not in the spinal cord area. This could be any other stimuli. Here are some senses. We've got smelling and taste and touch and sight and hearing. Those are all the senses. Those are all special cycles of the nervous system that we showed. These are all have special ways of communicating with the brain and the processing centers. So that's pretty much all I'm going to cover there, because the peripheral nervous system, the somatic part, is stuff that you've already heard about. It's the moving the muscles, causing movement of joints, causing movement of the bones and limbs. It is the things that we've already experienced in life. I'm going to focus more on the autonomic or the involuntary part, because there's some other parts I want to get to that you may not have heard about. So all the stuff we didn't talk about, the autonomic, the involuntary part, it has two parts. It is sympathetic and it is parasympathetic. And we'll get to the difference there. But these control the things you can't control yourself. These control the breathing, the heart rate, liver function, spleen function, kidney function, adrenals, pancreas, gallbladder, digestion. All that stuff is controlled by the autonomic nervous system. And the two parts, one is stimulatory and one is depressive. One is fight, flight. The other is rest, relax, digest. And so those always have to be in a balance. So we go back to that system diagram, and there's always an on and an off. So if you get too resting and relaxing and digesting, you can't fight, flight. And if you get too fight, flight, you can't ever rest, digest, heal, and process. So those have to be in balance, and those have to have an on and off, and they turn each other on and off. But then you have the decision maker and other stimuli affecting that. So I want you to be aware of what's going on here. Here's a more complicated diagram, and again, it's not full, but you can see the sympathetic and the parasympathetics affect everything in the body. Every cell in the body is affected by this. Even the motor nerves are affected by the sympathetic, parasympathetic. When you get into fight, flight, when you get scared, when something stressful is happening, your muscles get ready to act. And so it even affects the voluntary muscles. Here's a better diagram. Again, it's just showing the complexity, and this is not anywhere close to how complex it really is. And here we have the sympathetic and parasympathetic. I'm going to park here for just a little bit because this is the fight, flight versus the rest, relax, and digest. So you can see on the left, the sympathetic, this dilates the pupil so you can focus a little bit better, a little bit more tunnel vision. You don't salivate. Saves the hydration for the muscle use. It relaxes the bronchi, opens them up so you can breathe better. Your heartbeat starts to increase so that the oxygen is getting to the muscles. Digestion is stopped because those resources might be needed to run fast for a little bit. Glucose production is increased, which gives, again, energy to the muscles. Adrenaline is increased. Noradrenaline is increased. Those are hormones, which we're going to talk about in just a little bit, that increase the output of muscles. Bladder contraction is stopped. So if you don't have to stop and empty your bladder because that might get you eaten by a lion. So this fight flight thing really gets you prepared to either fight or run away. The parasympathetic does the opposite. It constricts pupils. So it constricts. It narrows them down, so you're not seeing as much. The dilate is the other way. I'm sorry about that. I said that wrong. The parasympathetic stimulates the saliva. It slows down breathing. It slows down the heartbeat. It stimulates digestion. It stimulates processing whatever food you got in. It stimulates getting rid of the stuff in your body. And it just stimulates you in a way to slow down so that your body can regenerate and rest and heal. So you have the sympathetic fight, flight, I'm going to catch my food. Then you have the parasympathetic is, I caught my food, now it's time to eat it. And so you have this balance going on. If there's an imbalance, if something is interfering with that balance, you're going to be in either a parasympathetic dominant or a sympathetic dominant state, and that's not good. That's not good at all. So that's how that all works. And again, I've kind of flew through that. That's the normal content of a nervous system lectures that you're going to get in school. I thought I'd give you something a little bit extra. And so we're going to talk about how the nerves and the hormones interact and how they're actually part of the same system. Because the nerves are the communication system of the body, but so are the hormones. The endocrine system is a slow-acting, universal, which means it affects every cell in the body, communication system. So when you have adrenaline released by the kidneys based upon a signal from the brain, every cell in the body takes that adrenaline signal as a time to get ramped up, ready for action. And that's what happens. It's slow. It takes a while to drain down. If you are sitting watching TV and a lightning bolt or a thunderclap happens really close, you're startled. And it takes you a little bit of time for that chemical epinephrine to wear off in your body. So you're going to be 5-10 minutes before you can calm down. And that's part of the reason the endocrine system is not the main system. It's a supplementary ongoing system, so the brain can stimulate it, get you active, but then it can go on to handle the other things that it needs to do for whatever reason that it was stimulated in the first place. The endocrine system is made up of glands, and the glands release hormones or chemicals directly into the bloodstream. And again, these chemicals are specific for certain actions within the organism, throughout the entire organism. The master gland is the pituitary gland. And the interesting thing about this is it is half nerve and half gland. It's called the master gland because it interfaces and interacts directly with the brain. Some people consider it part of the brain, other people consider it a gland, and most people consider it both. It is where they have this direct, singular contact between the two. And it is also the master gland because it sends out the trigger hormones as well as the electrical impulses. It doesn't send it out, but in addition to the electrical impulses sent out by the brain and the central nervous system to the other glands, the pituitary gland sends out chemical signals to them as well. So they get an instantaneous jolt by the central nervous system, and then they get a chemical jolt or a sustaining signal from the pituitary. So this is a very, very important part of the central nervous system, the master gland of the hormone system, and they are part of both. It is part of both. Thyroid's part of your gland. You've heard about the thyroid. It regulates the body metabolism. The pancreas regulates glucose metabolism and storage and release. The adrenal glands, that sits on top of the kidney. We've already talked a lot about the adrenal glands and the adrenaline and the norepinephrine that they release. Ovaries and testes, these are also organs that regulate how reproduction happens. And so those are also part of the hormone system. And the pituitary gland hangs off here, right off the part of the hypothalamus, where all of these things are coordinated and controlled. And like I said, it is part of the brain. It is the master gland of the hormone system. And it's part of both, and it's an intricate part of both. So here we go. We have this decision tree that we talked about being part of being how the brain or the nervous system works, and here we have the hormones. And then we realize that the hormones, or the decisions we make, can also release hormones. So a decision to watch a scary movie can cause us to have a epinephrine or adrenaline release. And that adrenaline affects every other part of the system, including the next decision we're going to make. So we can see how they're interactive and they depend on each other. So I don't want to minimize this, but after we've talked about it, it should be kind of clear that this is getting kind of complex. And it should be. We're a very complex organism. We're made up of trillions of cells with many different systems. Every cell has a function, and those functions determine what tissue it's part of. And the functions of those tissues determine what organ it's part of. And the function of those organs depends on what system it's part of. And that system that we're talking about here is the central nervous system, or the control system. And hormones, even though they're a separate system from the brain, brainstem, spinal cord, they function together. And that's why I call it the neuroendocrine matrix, because they work together even though they tend to be separate when they're thought of in our body. Because again, what we knew before isn't the truth anymore. We see these working intimately together, and we can't really separate them as separate tissues anymore. And so what do we do with that? We process it in a different way. And we're going to see that again here in just a second. I'm going to call this the psychoneuroimmune matrix for a very specific reason. There's actually a degree you can get, a PhD in psychoneuroimmunology. It is a relatively new. It's only 30 or 40 years old, but scientists started to see the way we think affects the way we do, which affects how our immune system responds. So let me see if I can diagram it out this way. So we already know about our decision tree. I'm just going to represent that with here. This is a normal cycle. We talked about it, how the brain works. We already know about the hormones and the decision tree work back and forth together. We just saw that. We know that our thoughts affect the decisions we make. If we are, every time we see a red truck, we think of the time that we saw a red truck slide off the road on the ice. And so those memories prepare thoughts, and we make our decisions to get ready to go help somebody out of the ditch because we saw a red truck. It has nothing to do with the reality of that moment, but has to do with thoughts and memories that we had before. Those decisions affect our hormones, and our hormones affect our decisions. So you can see what's going on there. Do we know how or why? Not yet, but it doesn't make it not true. Then we have these other things called feelings. They're not quite as concrete a concept as thoughts. I can think about a red truck driving into the ditch or ending up in the ditch. That's just a statement of fact of something that happened. How I feel about it is something totally different, and that may not be able to be put into words, but we definitely have feelings about it. Some people get anxious, some people get excited, some people get a feeling of I don't want to say joy, but joy because yes, the truck went in the ditch, but nobody got hurt, and that was Grandma. And so, yeah, that was horrifying, but it was also great. I feel really good that red truck, because of the way it was built, I feel really glad that Grandma was in that truck because she wasn't hurt because she was in that red truck. So our feelings don't necessarily fit with the thoughts, but definitely affect our decisions. And our feelings do affect our thoughts, and they kind of go back and forth. So that's kind of why I made this complicated diagram here. It's because these four things interact with each other. Do we know how? No. Do we know why? No. But we know that they do. And if any rational person looks at it, they'll say, yeah, but we just don't know why, how yet. And then, of course, that affects everything else. So we already know this. So this is a psychoneuro endocrine kind of matrix here. Now what we're finding out in the last 20, 30 years is this immune system that we all have also affects the hormones directly. The hormones affect the immune system feedbacks to the hormone glands. The decision, the brain, the brainstem, spinal cord, all that processing, all of those decisions, how we think about things, directly affect the immune system. The immune system directly affects our decisions. If we know that we go to this area and we just end up our heads being all stuffed up because our immune system got attacked, we just don't like going to that area anymore. Like for me, I love Kentucky, but Eastern Kentucky in the spring, summer, I just don't go there because I'm allergic to the bluegrass pollen, and that just tears me up, and I can't breathe, and I just get ugh. So this immune system triggering thoughts and feelings and memories makes me make decisions so that my body is protected. Definitely affects my hormones. There's a lot of stuff going on in the immune response that affects the hormones. It's just a complicated matrix. And the immune system does affect cell actions down after it gets input. The immune system can counteract or enhance whatever the normal action is at that target cell, and they interact together. So you can see this is a very complex thing here, but all it is a bunch of circles on how things are done. And so this is a complex normal cycle, if you will. But here's the interesting part. Some people say that the immune system is actually the imperial guard for all of these systems. Its function is to protect the brain, brainstem, spinal cord, the hormonal system, control system, from everything else. And the tissue cells outside here are only time they're protected is to protect the nervous system. And so that's another layer of thought for you. Um, I hope this was instructional. I hope this was somewhat entertaining, making fun of me and my technology. I hope that you got a concept, an overview of what's going on in the nerve system and how very complicated it is. And I do hope that you come away with this notion that we know certain things, but there's certain things we don't know. That doesn't mean they're not true. It doesn't mean we shouldn't explore them. It just means we don't know about them yet. I do hope that some of this was new information. And if it wasn't new information, I was hoping it put it in a different way so that you could understand it a little bit better. And this list of research is just a very short list of just the psychoneuroimmune complex that I described in the last 3 slides. A lot of research out there. What I gave you, nothing I gave you today hasn't been talked about before. I just hope that this filled up an hour of your time. I hope you learned a little bit. I hope that it was beneficial for you. One last thing I really want to leave with y'all is I do hope that this time of stress, you guys hunker down with each other. If you're a little bit scared about what's going on in the world, rest assured you're not the only ones. Your mom and dad might be a little bit scared too, and that's okay. This is new, and yet it's not. These viruses have been around for a very long time. These viruses have been part of human history for thousands of years. We as a species survive, but we still need to be smart. We still need to be kind. We still need to be caring. And we need to talk with each other, make sure that we're not messing up our thoughts. Let me see if I get there. We need to make sure our thoughts and our feelings are giving us the best immune system possible by being positive. Because if your thoughts and feelings go negative, it produces negative decisions, negative hormones, and that dramatically reduces your immune response. We need to be thinking positive thought. We need to be spending good time with our friends and family. And we need to be reaching out to those around us in the community. So talk with your mom and dad. Talk with your brothers and sisters. Let them know it's okay. That this too shall pass. And we'll get through it together. If you have any questions, give me a call. Or reach out to me, DocHoskins@live.com. Reach out to me on Facebook. Thanks for your time. When I end this, it'll automatically be saved for YouTube. So if you thought of any value, let people know they've got an hour of the nervous system if they want to spend their time doing it. Thank you much. Love you guys. Bye-bye.